open to Sturm-liouville problems. Before we introduce an important solution method for PDEs in the next section, we consider an ordinary differential equation that will arise in that method when dealing with a single spatial dimension x, the Sturm-liouville or SL differential equation. Let P, Q, and sigma be functions of x on an open interval from a to b. Let x be the dependent variable and lambda a constant. The regular Sturm-liouville problem, everybody mispronounces it as far as I can tell, Liouville, is the SLODE given here, where we should take note that x, capital X, is a function of little x, and we take the derivative with respect to x. The reason we have p in there is that p can, in general, be a function of x. So we need to use the product rule for the differentiation. We have x times q, and then we have lambda and sigma here, also multiplying x equals 0. So the Sturm-liouville problem includes, as well as this ODE, these boundary conditions with coefficients beta. So we have x at a and x prime at a in the first equation, and x at b and x prime at b in the second equation. So this is a type of boundary value problem. Okay. So typically in the past, your ODEs have had initial conditions, right, where they have to meet some initial condition or conditions. This problem has two different values, a and b, of the independent variable, little x, at which you can define conditions that need to be met for a solution. So it's a little bit different than what you've seen before. I mean, technically this is an ODE, but it's not an ODE that you will often see before you start solving partial differential equations. So it's a bit new to us. So I thought we would deal with this problem separately from the PDE problem, which will include Sturm-liouville problems as a subset of them, these boundary value problems, as a subset of the solution. So this problem has non-trivial solutions called eigenfunctions, x sub n, where n is a positive integer, corresponding to specific values of lambda, lambda sub n, called eigenvalues. Okay, so eigenfunctions and eigenvalues. There are several important theorems proven about this. Of greatest interest to us are that, one, there exists an infinite number of eigenfunctions, xn, unique within a multiplicative constant. So there is an existence of these solutions. Two, there exists a unique corresponding real eigenvalue, lambda n, for each eigenfunction, xn. And the eigenvalues can be ordered from a lowest eigenvalue, lambda 1, to greater ones. Eigenfunction xn has n minus 1 zeros on the open interval between a and b. So zeros are places where it crosses the value of 0, right? Or it could just touch it at 0 and go up. The eigenfunctions xn form an orthogonal basis with respect to weighting function sigma, such that any piecewise continuous function f over the interval can be represented by a generalized Fourier series on the interval a to b. Okay, so those are the things that are of interest to us. Okay, the last theorem in particular will be of interest to us in the next lecture. We're going to be constructing these generalized Fourier series from this fact that the eigenfunctions are an orthogonal basis. Okay, types of boundary conditions. Boundary conditions of the Sturm-liouville kind these guys, have three subtypes. Well, I guess I listed a fourth, which is not always listed, but four subtypes, we'll say. Dirichlet, and that's for just beta 2 and beta 4 equal to 0. So beta 2 and beta 4 being equal to 0 means that we've got a specified value of x of A and x of B, not the primes, okay? Neumann, for just beta 1 and beta 3 equals 0, so these two terms being 0. So we have the slope of the boundary defined. And Robin, which is for all of the betas being non-zero. So you have all of those as part of your conditions. And then mixed, so if beta 1 is equal to 0, beta 3 is not, and if beta 2 is equal to 0, beta 4 is not. So you're going to have at least one that includes a prime and a value. Okay, so those are the four types. There are many problems that are not regular Sturm-liouville problems. For instance, the right-hand sides of equation 7.3 are 0, making them homogeneous boundary conditions. However, these can also be non-zero. Okay, a lot of times the solution technique will still work, but you don't have the theorem that's proven that there will be a solution. It's not guaranteed. So another case is periodic boundary conditions, which says that the one end of it is equal to the other end, and the slopes are also equal at the ends. So those are periodic boundary conditions. It's also a non-Sturm-liouville boundary condition. So those are two possibilities. They're not Sturm-liouville. We can often still use the same technique, so it's important to realize that this theorem guarantees the existence of solutions in certain cases, but it doesn't exclude them in other cases. Okay, it doesn't say that there are no solutions if these conditions are not met. Okay, so you don't have the nice theorems that are helping you there. Okay, so what I'll do here is we'll start this example, and then I'll give you guys a few minutes to try to work on it, and then we'll come back and we'll do it together. Okay, so consider the differential equation x double prime plus lambda x equals 0. So I've set a few of those values up here to 0, or to 1. So like p is 1 in this case, q is 0, and sigma is 1. And the boundary condition I'll give is the Dirichlet boundary condition on the interval of 0 to L. I'll say that x of 0 is 0 and x of L is 0. Okay, so we have this sort of like pinned, if you're thinking about the beam boundary conditions, which is probably the only case that you've experienced a boundary condition discussion before, this was called pinned boundary conditions for the beams. But this is Dirichlet in general. So solve for the eigenvalues and eigenfunctions. Okay, so I'll give you guys a few minutes, and then we'll come back and solve